Oke.
Silakan Bu, bentar lagi dimulai. Saya akan mencoba untuk memasukkan beberapa peserta. Mohon maaf menginterupsi.
Oke.
Saya masukkan.
Problem.
Terima kasih.
In a few minutes, maybe we can start from the
Yeah,
expert.
no,
Yeah.
no problem. I mean,
Later, if you want, if you come to the Indonesia, please come to our office, and then
yeah, maybe next time I will start coming soon now that the new project starts in a month.
To make the connection, what the research still doing in your university, and then also in our office to make the connection, maybe later, yeah.
Yeah.
Looking for together to make the funding or something. I
Yeah,
think
yeah.
better.
Yeah,
Yeah.
I can build already on Sanjay's, with you, and maybe I can ask Sanjay about with which I don't know the name of the people he talked to in main brain, but we can kind of
Yeah.
reconnect also with those people.
Yeah. Okay, that's good.
Okay, maybe I can start.
Yeah.
Just show this in the meanwhile.
Monggo silakan Pak Bugi untuk dimulai.
Kenapa?
Ya. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good morning, ladies and gentlemen. Yang terhormat Pak Asep Hidayat, PhD, Head of Research Center for Ecology and Ethnobiology, BRIN. Distinguished speaker, Mr. Massimo Lupascu, PhD, as the main speaker in this expert talk. The first, from the Department of Geography, National University of Singapore, and Director of the Climate Change and Sustainability Program. Dr. Made Hesti Lestaritata, SSE, MSE, the moderator of this event. She is the principal investigator at Research Center for Ecology and Ethnobiology, BRIN. Honorable Zoom guests, respected participants, and beloved friends from various backgrounds, welcome to the first expert talk in 2025. It is a true pleasure and honor for me to be your master of ceremony today. We are gathered here not only to share knowledge, but also to foster dialogue, respect, and the possibility of future collaboration among us. The title of this first expert talk is Draining the Past, Rewetting the Future, GHG Dynamics and Management of Tropical Peatlands. On behalf of the organizing committee, we deeply appreciate our speaker, Mr. Massimo Lupascu, PhD, for his presence in Zoom room. We hope this event becomes a valuable platform for learning, discussion, and inspiration for us all. Let us now begin our journey together. Once again, welcome and thank you for being here. Now, with great respect and honor, we would like to kindly invite Mr. Asep Hidayat, PhD, the head of Research Center for Ecology and Ethnobiology, BRIN, to deliver his welcoming remarks and open this event officially. Sir, the time is yours.
Yeah. Thank you, Mr. Tony, from deliver the time to me, and then good morning and warm gathering to all of you. Distinguished guest, esteemed speaker, Dr. Massimo Lupasco. Maybe I can call
Max.
Dr. Mac, yeah. Maybe no better, yeah. Thank you. And then also researcher, practitioner, student, and then follow our colleges. And then it's a great honor and pleasure to welcome you today and our webinar with the title Draining the Past, Rewetting the Future, Greenhouse Gases, Dynamic and Management of a Tropical Peatland. On behalf of our committee, we extend our sincere appreciate for your participation in our important event. Maybe in the I call is the expert talk. Yeah. Today is the session 1 at 2025. As many of us here understand, tropical peatland play a pivotal role in the global carbon cycle, covering a relatively small fraction of the Earth at the surface. They store amount of the carbon accumulated over 2,000 of the years. When these peatlands are drained, whether for agriculture, plantation development, or another use, they'll become major source of the greenhouse gases emission, contributing significantly to global warming and also ecosystem degradation. This expert talk, we have some purposes. First is to explore the complex dynamic of the greenhouse gases emission from the tropical peatland. And second, discuss play for sustainable peatland management, especially through rewetting and ecology restoration. The title of the webinar or expert talk today is Draining the Past, Rewetting in the Future. Reflect not only scientific and the policy challenges, but also collective responsible to restore what has been damaged and ensure a better ecology future. We also deeply honored to have with the today to Mr. Mac as a leader expert in the peatland ecology and greenhouse gas plugs. He has significant advance as understanding of the biogeographical processes in tropical peatland and how manage the practices can influence emission. His insight today will be crucial in the guiding us discussion and informing practical solution from the peatland conservation and climate action. We hope this expert talk will serve as the platform from this discussion, knowledge exchange, and the collaboration across a section on discipline. Let us take this opportunity to frame our shared commitment to protecting and restoring tropical peatland from the climates, from the diversity and poor community that depend on them. With that, we would like to officially open this expert talk and invite you all of you to engage active in today's section. That's all. Thank you very much. Thank you very much and enjoy in the expert talk. That's all. I give the time to Mr. Bugia. Thank you.
Thank you, Pak Kapus, for your welcoming remarks and opening this first expert talk officially. Ladies and gentlemen, as we move forward with today's agenda, it is now time for our main session. To guide the discussion and ensure everything runs smoothly, we are honored to have an excellent moderator with us. Please allow me to introduce Mr. Dr. Hesti Lestaritata, SSE, MSc, who will be leading today's session. Hesti Lestaritata is a principal researcher of Research Center for Ecology and Ethnobiology of the National Research and Innovation Agency, or BRIN. She is a PhD graduated from Utrecht University, the Netherlands, with educational background of plant ecology and biodiversity. She has wide working experience in the lowland tropical forests and peatlands. In the field of ecology, silviculture, agroforestry, and paludiculture. She also familiar works with farmers and local stakeholders in the implementation of research action projects. She published many scientific articles in various international journals, book chapters, several books, proceedings, and national peer-reviewed journal. She also serves as a co-promoter and student's mentor. She is an active member of several professional organizations such as International Peat Society or IPS, Perhimpunan Periset Indonesia or PPI, and others. Mr. Hesti, Mrs. Hesti, the floor is yours.
Yes, thank you, Pak Buki, as a MC. I think you forgotten one important thing, event. We should have a picture together before Pak Kapus, before Pak Asep arrive for other meeting. Would you like to leave or
Yeah, Mrs. Chike will help us to take a photo in this photo session. Please, everyone, open the camera so we can have all together in the good performance of photo sessions. Thank you very much, Mbak Chike. Please, your turn to take the photos. Everyone, please open the camera and please the best of your smile.
Okay, Pak Buki, I'll start with first screen. Okay, second screen. And the last screen. Okay, thank you.
Thank you.
Bu Hesti, maybe I cannot join in the until the end of the expert talk because I have this another agenda. Maybe I will leave expert talk today. Yeah.
Yeah. Thank you very much.
Thank you, Pak Kapus.
Yeah. Mr. Mike, I'm so sorry I cannot stay in the long time.
I understand. That's okay.
Yeah. Thank you very much.
Thanks for having me.
Yeah. Thank you very much. Assalamualaikum.
Yeah, okay, thank you very much. So now, thank you, Pak Bugi, MC, and for the opportunity and introduce me to the audience. And ladies and gentlemen, very good morning. I'm delighted to be a moderator for today's expert talk. Greetings to you all. Let us be grateful for our continued health and the opportunity to continue improving ourselves and being productive. Ladies and gentlemen, welcome to the first expert talk in 2025, hosted by the Research Center for Ecology and Ethnobiology, National Research and Innovation Agency, BRIN. This time, we are going to listen a very interesting topic regarding our current environmental condition, particularly peat ecosystem. As mentioned earlier by Pak Kapus, the peat ecosystem play a vital role for the life of human beings and other creatures. They provide ecosystem services, mostly for the storing carbon as regulating services. And tropical peat formation is based on the accumulation of organic matter, and it is also known as a fragile ecosystem. Peats are easily damaged by natural and anthropogenic disturbances, such as peatland clearing, canal development, fires, and once peat are disturbed, they release greenhouse gas emission into the atmosphere. So how does the conversion of forest cover to other land cover, such as industrial monocultural plantation, affect the carbon dynamic? How does the biogeochemical pathway of methane and carbon cycle in peat soil and peat water in clear peatland? Why does methane gas increase when peatland are cleared and canal are developed? And what are the dangers if peat ecosystem are left to deteriorate? And how can we mitigate and restore peat degradation? Furthermore, based on those research evidences, what policies are relevant to climate change and tropical peat management? So in today's seminar, we are delighted to invite a prominent scientist on tropical peatland to share his knowledge and recent research findings and to bring solution for peatland management in Indonesia, Mr. Massimo Lupascu, PhD. Let us introduce our research person, Dr. Massimo Lupascu, we call Max, yeah, Pak Max, is an associate professor in the Department of Geography at the National University of Singapore and director of the Climate Change and Sustainability Program. Before joining NUS, he spent nearly a decade researching Arctic peatland and permafrost, focusing on how thawing soil affect carbon emission. This transition to tropical system brings a valuable comparative perspective on carbon vulnerability across climates. At NUS, his research investigates how climate and land use change impact carbon cycling in tropical peatland. He uses a combination of field-based greenhouse gas flux measurement, stable and radiocarbon isotope analysis, microbiological techniques, and hydrological monitoring to trace the sources and controls of carbon emission. Dr. Max holds a PhD in physical geography from the University of Bristol, UK, and has held academic and research positions in Italy, the United States, and Singapore. He's going to present a lecture entitled Dreaming the Past, Rewetting the Future, Greenhouse Gas Dynamics and Management of Tropical Peatland. You will have about 30 minutes for presentation, Pak Max, and afterwards we will continue with a discussion. And this will spread into at least two sessions or even more if we still have enough time. And the first session, we will select 3 participants to ask questions directly to Dr. Max, and then continue with by the second session with 3 questions from the chat room. And ladies and gentlemen, be ready and be focused on listening to the lecture. I welcome Dr. Max to give his presentation. So now, time and screen are yours, Pak Max. Thank you.
Thank you so much. Thanks for having me, and thanks for the nice presentation. I'm very happy to be here. I'm very happy to present some of our recent data from my group. I might talk for a bit more than half hour. I don't know
It's
if
okay.
Okay, because I saw that we had enough time.
Yeah.
At the moment, the presentation probably is more than half hour. But Hesti, if you tell me that I have to cut, just tell me it's fine. I can kind of skip some. I can skip some slides if I talk for too much. Anyway, as I mentioned,
Yes,
thanks again for having me. I mean, what I'm gonna talk today is, as I mentioned, some of our recent results from our integrated tropical peatland program. So I decided to frame our papers. I mean, 2 are already published, and 2 I will show some of the results are not published yet. So I decided to create a storyline that hopefully you will enjoy, kind of starting from the bigger picture and then slowly kind of zooming in into the ecosystem processes. So the data that I will show you today are from postdocs in my group. So then if you have very specific questions, hopefully I will be able to answer. Otherwise, I will ask my team members to answer the more detailed questions you might have. So the good thing is that because I'm now doing this kind of brain seminar, I probably have to skip a bit of the introduction. That's why I decided at the moment I just put 2 slides, but everybody knows what peatlands are, so I don't think I have to go into the details of the importance of peatlands too much. So I will just give a couple of slides. I would rather focus my time on the actual results. Okay, so starting, of course, I mean, just really briefly, as also was mentioned by the chair before, peatlands, despite occupying a very small amount of land, we're talking about only 3% of our land. They store very important numbers in terms of carbon, about 600 gigatons. That is equivalent to 31% of the total organic carbon pool, right? And of course, I mean, when we talk about geographical areas, northern peatlands occupy the majority of this area. but also in the tropics, if we look at numbers, they cover 44 million hectares and they store about 100 gigaton. And of course, we know a lot about Arctic peatlands already, but the focus over the last few decades, and I'm so glad about this, I start focusing more and more on the importance of the tropical peatlands. So I feel in a very privileged position to to be able to stay in Singapore and surrounded by countries like Indonesia and Malaysia, where kind of allow me to do hopefully some great science and great research. There's still so many questions that needs to be answered. So we're kind of feel really privileged to be living in this part of the world and try to answer some very important research question. As I mentioned, of all these tropical peatlands, around 40% of these tropical peatlands are located right here in this part of the world. And of course, as you know, Indonesia has the major extent of these peatlands. The formation of these peatlands in this part of the world started around 8,000 years ago, and this period saw rising sea level that create, of course, extensive lowlands and floodplains for the formation of these peatlands, thanks also to very stable and humid tropical climate that allow the growth, of course, of a lush vegetation and a very slow decomposition that allows deposit of peatlands of up to 20 meters, especially here in Indonesia. So I'm going to focus basically my talk on the kind of some of the latest results, as I mentioned, from Indonesia, where my research focus. I mean, I work also in Malaysia and Brunei, but I would say over the last few years, my focus has been more in your country. We know, of course, when we talk about Indonesian peatlands, about the problems, of peatland degradation due to drainage, right, for creation, right, of agricultural land for pulpwood plantations and oil palm plantations, right, and as we are very familiar with, this drainage of these peatlands leads to important carbon emissions, and also the chance, of course, of having fires that leads to even more carbon emissions. So the kind of focus on my research is, was mentioned already by Hesti before, is kind of trying to understand what are the impacts of this kind of when you change an intact forest and you change it to a different land use, what's happening in the soil. I'm kind of focusing really my research on kind of the carbon dynamics of these peatlands, but at the same time, my research is trying to look also at the big picture. So I like kind of combining, focusing on trying to explain ecosystem processes in peatlands, but also looking at the big picture. So one of our most recent paper that was published only a few months ago on Nature Communication, and that was led by probably a name that you're already very familiar with, is Sigit Sasmito. He was a postdoc with me for 3 years during this integrated tropical peatland program, and now Sigit is in Australia he has his own position now in Townsville. So now I'm gonna present some of the data from our work when he was a postdoc. Here with us in US, where basically he kind of tried to look at kind of refining all the numbers on carbon emission and the deforestation for the entirety of Southeast Asia, and looking both at peatlands and mangroves. But of course, because this talk specifically focus on peatlands, I'm going to show you results. Of course, mainly just from peat swamp forest and not from mangroves. Also, because the most interesting results, of course, in terms of numbers, were from the peat swamp forest. So some of these kind of numbers were kind of also quite surprising for us. Some are kind of more familiar, but others numbers have been quite revised compared to previous assessments. So I hope you will find this useful. And also, I mean, this paper has already been published. So if you want kind of more the details, kind of numbers, everything is already on the paper. But basically, what we've seen is kind of looking at data from up to 2022, so very recently, so over the last 15 years. We've seen that in terms of deforestation for the entire Southeast Asia, about 12 million hectares of peatswamp forest has been cut, and of this total of 12 million, 74% were converted to tree plantation and oil palm plantation. So the total of the 74%, 47% is just for the plantation. Another interesting, and so these are kind of a bit of refined numbers compared to previous estimates. Some kind of interesting numbers are actually from the drainage canals, is that it's a component that actually is not really in majority of the assessment, it doesn't show the drainage canal. Then you will see that this number, while here show you 2.5%, but then when we start looking at the carbon emission, you realize how big is extremely important also to take into consideration also that component. Sometimes, we just, of course, because of the area, we focus mainly on the plantation, but also the surface of the drainage canal also is extremely important when we start looking at adding all these numbers in terms of carbon emission. And of course, the remaining 26% has been converted to other land uses. So if we start looking at these areas in terms of carbon emissions, we can see that 48% of Southeast Asia land use carbon emission comes from peatlands and the mangroves. So this is a very big number, and especially if you think about to put this number in the context of what are the different type of land covers that we have in Southeast Asia, and peatlands are only 5.4%. So if you think that only 5.4% of land area can emit up to 48% of the entire land use emission, then kind of that numbers kind of course it's a bit quite important, very significant, right? And of this number, Indonesia and Malaysia account for 85% of this emission. That's quite normal because if you think about the extent of peatlands, of course, Indonesia is first, followed by Malaysia. Okay. Looking at again refining these numbers and looking also at the importance of this area that I will show you in a minute with a few other slides, was driving the emissions of this was driving the emission of peatlands. So the total, as I mentioned here in this slide, we're talking about almost 700 teragrams of CO2 that were emitted over the last, sorry, not 15 years, over the last 20 years. But if we start looking, in terms of percentage of what are the sources of this emission, based on our estimates from looking at the entire Southeast Asia, we can tell that almost half of this emission comes from peat decompositions. And then from deforestation, only about 23%. So you can see already here some interesting numbers, right? Normally you would imagine that deforestation from emission from land cover change would be the majority but actually in peatswamp forests, as you can see here, peat decomposition are the majority, about 46%. Then of course we have peat fires, that's about 20%. And then here we have an interesting number that normally you don't have, has not been mentioned in many of the reports that we have around. That is the emissions from canal drainage and excavation. That is almost about 10%. So also our numbers, if you compare the 700 teragrams compared to previous estimates, our numbers can be a bit higher compared to other estimates. And one of the reasons we think is, of course, we have a refined numbers in terms of area, and of course that's affected, the final number. the fact that many of the papers before did not include this kind of drainage and excavation is about almost 10%, and some other reports did not include pit fire. So if you take into consideration all these factors, then you should not be surprised that some of the numbers that are mentioned here are slightly different from previous estimate. On the right, you can see one of the key figure from the paper. Looking, these numbers on the left represent the entire of Southeast Asia, but then our paper also looks at the specific country. So we hope that some of these numbers will help each country. We know that soon we'll have to each country will have to submit the NDCs, the National Determined Contribution, and we hope that some of this number will help practitioner policymakers kind of to when they do their assessment for the NDCs. While in Indonesia, we are kind of not too surprised about some of these numbers. We know already quite a lot in terms of science compared to other countries. But I think the interesting part actually is also coming from the other countries. Well, of course, we always focus on Indonesia and Malaysia, but actually some of the numbers from the other countries are also quite significant. Of course, I mean, for other countries, especially the one on the right, you can see Vietnam, Philippines, Cambodia. Those numbers, of course, the estimate is a bit more, is not as accurate as the one we have for Indonesia and Malaysia, because we're still kind of finding out exactly where peatlands up. So some of the estimates from kind of these other Southeast Asian countries, we still need to kind of work really on the mapping. While of course we have a better understanding of the peatlands, right, in Indonesia and Malaysia. But one of the takeaway message anyway from this slide is that emissions are not only from deforestation but also from the long-term decomposition of soil carbon pools. So this is definitely one kind of key message that I would like you to remember from this slide. Another very important part and component of this paper, and that was kind of the main take-home message of this paper, is the mitigation potential of peat swamp forests in Southeast Asia. And of course, we talk a lot about, of course, and the importance of restoration, right? That's something that, when we talk about the peatlands, the main talk is about restoration, but we have to remember, and this paper proved that actually conserving peatland actually can be even more important than restoring. Of course, we want to have them both doing at the same time, but this paper really stressed the importance of conserving peat swamp forests, because this paper shows basically that conserving intact swamp forests can prevent up to 662 teragrams of emission annually across Southeast Asia. And so this accounts for about 86% of the region's total mitigation potential. So we're talking about a huge number. So if you look at this, the panel A, where we put into context, the global land use change emission, the Southeast Asian land use emission, and Southeast Asian peat swamp fund and mangrove emission, you understand the mitigation potentials coming from peat swamp forest is extremely important, 86%. Restoration, of course, is also very important, but we're talking about only about around 100 teragrams of CO2 per year. So within the restoration, peatland rewetting of oil palm and plantation, for example, we're talking about, this is 66% of this potential, while the remaining 33% is revegetation of degraded peat swamp forest. Of course, again, if we look at numbers, if we compare across Southeast Asia, again, because Indonesia has the biggest extent, the mitigation potential of this number, right, that we see here, Indonesia, for Indonesia, for the total of Southeast Asia is about 73%. So you can really tell how the importance really of conserving peatlands, especially Indonesia, has a huge potential for the entire region. So these are extremely key number, right? Because I mean, we normally, again, we discuss our discussion about peatlands focus mainly on the restoration component, but this paper stressed again that on the top of the importance of restoring peatland, even conserving peatlands can account for a huge number. Again, 86% of the region, 770. Of course, I mean, because I'm doing this seminar here in Brin, Indonesia, I'm focusing, the angle of my talk is focusing a lot of on Indonesia, obviously. But I would like you also, because I don't have that much time to go through each country, but I would like you also kind of to look some of the numbers from, of course, from the other countries. Again, looking also, for example, in Brunei or Cambodia or again Indonesia, you can see when you compare the mitigation potential in terms of percentage for each of that country, you can see that conserving peat swamp forest and mangroves can be even more important than restoring them. Again, it doesn't mean that you don't have to, of course, restore peatlands. I'm just saying that conserving, you should do, of course, both, but conserving can be even more kind of, if you have to choose in terms of how much money you have, and you say, okay, I can choose just between two projects. I mean, conserving a bigger areas of peat swamp forest has a higher cost benefit, and so you get more for your bucks. I mean, this is what I'm saying. You get more for what you spend in return. Okay. This is kind of one of the key aspects. So if we look now at kind of zooming in on the restoration part and comparing, the different type of land use type, of course, you can see that of course, if you have to again invest money on where to restore, which type of land use type of peatland you should spend money to restore. You can see, of course, that in terms of numbers, tree plantation and degraded areas are the one that you will get more out the investment, the best return of restoration you will get out for your bucks. Tree plantation, industrial oil palm, and degraded peat swamp forests. So here it's kind of pretty clear. From here you can see the revegetation and rewetting potential area for 1,000 of hectares, and also the emission reduction potential if you look at peatland rewetting in blue versus peatland revegetation. You can see how the rewetting again for tree plantation, if you add them all up, it has the highest potential. So here is kind of, we break down compared to other papers, we break down for each land cover the potential for each of the different peatland land covers. So this is quite a very unique study that really hopefully people, policymakers will find it very useful. Again, just summarize these efforts too of conserving and restoring peatland could cut forest follow emission by 54% in Southeast Asia and 16% globally. So we're talking about really big numbers. So in terms of recommendation, of course, many things you're already familiar with. But what kind of some of the findings in on this paper in terms of recommendation that we could give in the context of Indonesia. Of course, conservation, as I mentioned, based on the data, is extremely important. So recommendation to strengthen legal protection and expand conservation areas. Also in terms of water table regulation standard, we know we're familiar in Indonesia, there is the 40 centimeter water table depth minimum. Based on this paper, I'm looking at both CO2 and methane emission. We show that 30 centimeter could be a better mitigation balance in terms of trade-off between CO2 and methane. And also, actually, I will go into more details with this, with some of the other findings from other papers, because again, I mentioned this one looks kind of at the big picture. It's kind of many data, right, from the entire region, right? Also rewetting on industrial plantation that is not mandate for concession areas. So regulate, incentivize rewetting would be extremely important. And then also for aquatic emissions, also that's something that would be very important to include in the national inventories. I mean, I show you, right, for example, of the canals that cover about 10%. There in terms of emission, are 10% of the total, so big numbers. And I will show you also in some of in our other papers. We'll kind of go into the details of the aquatic carbon emissions, and you will see it's quite striking. Really, some of the numbers that we show from a palmwood plantation in Sumatra, really extremely important to look also at numbers coming from the aquatic carbon emission. And also this paper, they look again at the big picture, kind of go in that direction. So I mentioned until now, from this study, I showed you really the big picture. And again, I focus mainly on some key big numbers, but also some key numbers specifically from Indonesia. But our paper really covered the entire ASEAN region. So, and also, if you're interested in mangroves, please have a look also at that paper, because we cover both ecosystem. But of course, big numbers are important. That's why I put that first, just to show you the bigger picture. But how do emission happen? What's the role of water table? I mentioned the water table, the 40 centimeter versus 30 centimeter as a kind of recommendation. But kind of, you might wonder, okay, but can you go into more details with this? What does really show kind of these differences in water table, how they affect, the carbon age and carbon emission and so on. So the next part of my talk will kind of start zooming in some of these aspects with some other specific studies. And we did this basically through this integrated tropical peatland research program that we started right at the beginning of the pandemic, the worst time you could start a big project. As you can imagine, we started with a big delay, of course, because we couldn't go to Sumatra, where we had our field site. But basically, the idea, kind of in a nutshell, the idea of this project was to improve our understanding on decomposition and revegetation processes across a range of scales and tropical peatland use. So we had different groups focusing on different aspects, from really people looking at the big picture and using remote sensing, so satellite images, to people like me that I'm a soil biogeochemist by training. So I was the PI for focusing on the terrestrial and aquatic biogeochemistry component. Then the other PI, Prof. Sanjay Swarup, that he's focusing on the microbiology aspect. So really going from the sky to the soil and to the microbial level. So really many different sides. Of course, this was done in collaboration with APB University, as you're kind of very familiar and very close by, in Bogor. So we're kind of big team, as you can imagine. So in US, it was like geography, where I'm based, and NERI, the environmental research institute. So a big team trying to answer hopefully important research question then people working in the peatland field would be able to use, both policymakers and people that are in the field managing those peatlands. So I'm going to show you some of those results now. So if you're interested, I don't have the time now to show the video, but if you then click on this video, there is a kind of a short trailer, if you want to call it, of our program. So the project ended last year. As you can imagine, now we are writing. We had few papers out, and these are the one I'm presenting here. Some others, of course, we are kind of in preparation, working on. And again, there are many papers coming from each of these different groups. I'm going to show you here, of course, papers from my group, but I will show you also one slide from another paper that I'm involved. But I mean, I'm not the main PI for that paper. I'm just a co-author. But I think the results are on the vegetation aspect and I think you will find it very useful. So that's why kind of I decided to include at least one slide from my colleagues in the working on the vegetation part, and I'm kind of one of the co-author on that paper. So we worked on two different pulpwood sites. It's kind of two of the biggest company right in the world, dealing working on that produce pulpwood, April and APP, both in Sumatra. We focus on we had different research questions for each site. So I'm going to present some of those results in this presentation. So if we start talking about our TPJ site, that is this one here, the Tripupujaya site. There've been already some research there before, thanks to Al Huayer, that some of you are very familiar, is a very big expert in hydrology, and that's kind of thanks to him that we got introduced to a PMP, and because he had some results already from the area, we decided to build on what was already done there, to kind of have a bigger picture and more data. What the data that Al had and that I'm showing you here, and that was kind of what sparked the kind of our interest to work in the area, is that he had data for many years. We're talking about really 7 years of data on water table and subsidence from that plantation, and you can see the different colors here, showing side. Of course, the green one represent the more control, the kind of more intact side, swamp forest, and you can see then the one more dark brown and lighter brown representing site that were kind of degraded and then kind of rewetted. So this kind of data really show kind of how the importance of rewetting site in terms of subsidence. You can see, of course, if you start looking at the brown, that show the least rewetted site, the one really kind of they tried but did not work out. The rewetting, you can see how subsidence, starting at January, 2016, and where the last data I have here from a year and a half ago, maybe around March 2023, we're really talking about, from 0.1 meter to 0.65 meter subsidence, right? Really, really drastic subsidence of the soil. But you can see that where the site, well rewetted, here, the kind of this kind of brown here, kind of lighter brown, you can see that it's getting closer in terms of numbers, really close to the somewhat drained forest. I'm talking about somewhat drained forest because the two sites here, this one is closer to the concession, and the site, the more intact, is about a few kilometers in here. Okay, so that's why this site, despite still being forest, is still, of course, still affected by a bit of the drainage because just being so close. But you can see that this site here is very similar. The least rewetted site here is very similar to the intact forest that you can have here. So this kind of really show that where you do have rewetting, you're really getting closer to the original baseline of the peat. So these are data quite kind of unique because, of course, you don't have many published results that show data for such a long time. Normally, it's always like a couple of years, right? So having all this data is kind of extremely useful. So if we start looking, so we looked on this site, and this is the first kind of published data in terms of aquatic pathways. Now we move on to another site, the April site. Here they had a very unique experiment. As you know, for people that are familiar with dealing with the hydrology and keeping the water table at a certain level is of course, extremely difficult, right? But in this manipulation experiment here in April, they managed to have this gradient from shallow peat shallow water table to kind of deeper peatland that you can see here in kind of in this schematic here. Don't ask me how they manage to do that, because I have not, having this doing this is extremely difficult. But as you can imagine, we kind of some dams and so on, and a lot of monitoring of the water table. But the details of how they manage, because as you know, is extremely difficult. That's why the area is quite, it's not possible to do it for the entire plantation, but just for a specific area. So I would imagine that they use lots of dams in order to do so. But basically, we work on this manipulation experiment that the April the people working in April did, and we sample both the canals you can see here in blue. We sample the ditches. Here, you can see here's ditches like smaller canals, and pour water table on these two different sites, the shallower and the deeper. And we kind of try to compare, what kind of was happening in terms of aquatic carbon loss, looking at DOC, looking at CO2 and methane in solution, in the peat water. So what we found was extremely interesting. I mean, some of our numbers are some of the highest ever recorded. If we look at, for example, at the dissolved organic carbon that we found in the Acacia plantation, were among the highest reported. So the median was for about 46 milligrams per carbon per liter. We found numbers around 127, so extremely high. And of all the type of carbon pools that you have in the water, of course, you can measure DOC, POC, as I mentioned, CO2 and methane as gases in solution, right? DOC dominated the carbon pool. We're talking about 75% of the total dissolved carbon. Then with CO2 as the next most abundant, and methane. You can see here, starting with DOC, the comparison, the green represent the shallower, the site with the shallower water table, so closer to the surface. The red, the deeper, and then the blue, the ditch, and the gray, the canal. So what's here? Of course, you see the CO2. As you can imagine, CO2 was higher, right, in the samples collected by in the pore water from the two manipulation experiment, the water table shallow and water table deeper, and lower in the ditch and canal, because of course dilution here. And then methane, as you can expect, was higher, of course, in where you have water closer to the water table, closer, of course, to the where the water table was closer to the surface, going, of course, down in terms of numbers in the deeper water table experiment, the ditch and canal. So we saw basically how you can see in this number here, how water table depth, of course, influence gas emission, where shallow water table increase, methane emission, and decrease the ratio that you can see here of CO2 methane, suggesting, of course, a more anoxic condition. So this favor, methane production. And then going, of course, as you go towards, the ditch and the canal, of course, you have more of the CO2 dominated carbon fluxes. Another interesting result, of course, coming from the analysis of the radiocarbon. So here you have the fraction modern of, there's a way to measure radiocarbon. You can measure as fraction model or as a delta for DOC and CO2, and kind of take a message from this result shows that DOC and the CO2, so both, the carbon in solution as dissolved and the CO2 as gas, was around almost 500 years old on average. And so this, what does it mean? It means that suggests that old carbon is being released into in solution. So measuring the age of this carbon is extremely important, because if the age of the carbon is very modern, so kind of the last 60, 70 years. If it's modern, means basically that could be carbon that is just produced really from the plants. It's kind of recent carbon that is not really a net flux to the atmosphere. But when you have carbon that is extremely old, like hundreds of years old, that kind of tells us that the air is extremely degraded, because as you can imagine, as you drop the water table, you now have carbon that was locked deep in the peatland hundreds, sometimes thousands of years ago, that was locked there, and was happening, that was just there back then. But now, because of dropping of the water table, of course now microbes have access to that carbon that once was locked deep in the ground. And of course, once microbes start attacking, right, and decomposing the carbon, now that carbon is released into solution, or even as gas. So you can measure both in solution, but also as gas. And so that gives a very important number, because it tells that that all carbon now is released is a net flux to the atmosphere. So the more of this ancient carbon you have in solution, the more that's how degraded the air is. So of course, the older it gets, the older the carbon is, means that it's kind of really deep into the peat profile, and so the more degraded is the air. So it gives a kind of a lot of information on the kind of level of degradation of a specific area. So that's why it's important not just to measure the magnitude, how much the fluxes, but be able to measure the carbon 14. It gives a kind of a deeper understanding of the carbon dynamics. So if we move now to kind of another important isotope, that is carbon 13. Carbon 13 gives a lot of information of the sources of the carbon. Is the emission of the carbon is coming from diffusion? Is it coming from ebullition? Is it coming from plant transport? Or if we talk about methane, is the methane is produced, you have two dominant pathways when we talk about metagenesis. Is it coming from acetate production, hydrogenotrophic production? So again, looking at carbon 13 as well can give us kind of more nuance that goes beyond, saying, oh, this carbon flux is higher or lower than the other. Of course, those information are extremely important, but be able to have this data gives, again, like for carbon 14, gives a much more nuance. So the more nuance you have about the carbon dynamics, the more then you can do in terms of peatland, in terms of peatland management. So if we look now at the data, kind of trying to explain something really can be quite difficult. Hopefully, I'm going to explain it in a way that you can at least get some of the take-home messages. So if we start looking at the key point that we got from the carbon 13 data, we saw that of all the CO2 produced, of course, CO2 can be produced from respiration and from also methanogenesis. During methanogenesis, also you have production of CO2. So it's important to understand, is the CO2 coming during aerobic respiration, or is part of the production of the methane? Because again, you can have production of CO2 also during methanogenesis. And in our site, we saw how respiration dominates CO2 production, and that also the majority of the methane that we see kind of is kind of via evolution or plant transport rather than diffusion. Again, you can see it based on kind of the negativity of some of these numbers here. You can see both for methane, they can go from more negative to less negative. And again, that's the same for CO2. So knowing how more positive or more negative is one of these numbers, both for CO2 and methane, can give us all this type of information on the different pathways of methane, or the different type of methanogenesis that we have, hydrogenotrophic versus achenotoclastic. So also in our site, based on the numbers that you can see here, for methane, you see is kind of more negative. That tells us that it's more of a hydrogenotrophic methanogenesis. And also we see that, as kind of expected, this, of course, with shallower water tables, so of course, table closer to the surface, you have a more methanogenesis activity. But surprisingly, we see also still lots of CO2 coming, from also from respiration. This is only, of course, in the shallower water table because, of course, you have more anoxic condition. So, kind of, if you look at these kind of graphs here, I understand that my look can be complicated, but I mean that's why I put here these arrows showing that the less negative is the number, shows more oxidation of the CO of the methane here, and here left to right shows more if it's adrenotropic and acetoclastic. So kind of again, this in this slide really shows kind of some of the take-home message from some of these results. Again, so this is kind of results that were published from recently from my postdoc Pierre. Now he's at NTU, so you're gonna hear about him a lot, I think, in the next years a lot, because also he's interested as me in peatland, but he also works on mangroves. So he's gonna shows also he has some interesting results coming up also from some other studies. So this is another paper that Pierre is working on. This is at a different site. So the results I'm showing here was from April site. This was from APP site. And what we tried to look here was really comparing the impact of blocking a canal in terms of carbon emissions. We all hear about the importance, right, of damming the canal in order to rewet our peatlands. So here we had the chance we had access to one flowing canal, so where you have no dams, that you can see here from, just follow, the arrow. And then on the top, you have another canal where there was a dam. And so we had we were able to compare, a block canal versus a flowing canal. Again, for this, I'm not going to go into the details as I did before. I just want to show you one of the key result. So I have only one slide for this study that is in preparation. But the very interesting part is that if you look at DOC exports, so you have stagnant versus flowing, you have CO2 emission stagnant versus flowing, and methane emission stagnant versus flowing. You can see that it's in this side, blocking the canal reduced carbon losses by around 700 times. Really talking about big number here. You can see basically, I mean, the majority of the carbon, of course, comes from stopping, the DOC, the CO export. You can see the difference between the blocked and the non-blocked, and of course also on the carbon emission. What doesn't change too much is the methane emission. Of course, you have it in both sides, but as you can imagine, I mean, here you don't have the standard. The standard error doesn't show here, but in the stagnant, of course, stagnant water, you have a slightly bit more anoxic condition here, so it's a bit higher. But overall, of course, the interesting part, at least for these studies, is the stopping really of the DOC export and of the CO2 emission by blocking that canal. Again, there are more nuance, more data from this study, but again, you will hear more perhaps in the next year or so as we publish this data. So, key conclusion from this study. Again, acacia plantation and a carbon hotspot are major emitters of carbon, releasing a big amount, right, of DOC, CO2 and methane, but DOC, as you could see, that was the majority of the emission. You can see the importance of canal blocking. So blocking canals significantly reduce carbon losses up to 700 times. I showed you also how the importance of looking at the carbon age so looking at the age of the carbon, so it's extremely important to measure that. It's kind of 100 years old. That is indicated that deep carbon has been mobilized due to the drainage. Again, then the water table effects. this is kind of more expected. As you know, shallow water table increase methane production, but CO2 remains the dominant greenhouse gas due to aerobic respiration processes. In terms of the implication of some of these studies, the importance, of course, is to stress the importance of maintaining high water table to reduce VOC and CO2 losses. And in terms of climate policy, of course, aquatic emissions should be included, as sure counted in climate models to improve global greenhouse gas budgeting. So should be included also in NDCs. So in terms of restoration strategy, canal blocking, at least in our site, is an effective restoration tool, minimizing carbon loss and promoting carbon retention in tropical peat systems. So I've showed you now data from the aquatic component. So now I'm going to move to another study. Is led by Sigit. So I had Pierre that was focusing on the aquatic for my project, and Sigit focusing on the terrestrial. So what does the terrestrial data show us? So this paper is on currently under preparation, and I don't know how many of you are coming to Asia Flux conference. I will be in the April site near Pekanbaru in October. So I hope to see many of you. I will be there with many of our team and also a lot of other Indonesian colleagues. I will be in October, 20 to the 25th of October. So if you did not know about this important conference, please, have a look at the site Asia Flux. And of course, there we're gonna kind of show lots of this. Sigrid will present this finding, and Pierre are gonna focus on the other. So I hope to see some of you, or many of you, there. So to meet in person. So for the terrestrial aspect, the interesting part of this study, so of course many people measure carbon emission with the manual chamber showing here, but what we did that was quite different on this study, and was really going into zooming even more on this. And what we did, we took into consideration microtopography. So as you know, in a peatland you have more hummock and hollow, so you have difference in elevation in a peatland. So and of course this spatial difference is going to affect carbon emissions. So we decided to have a much more in detail spatial resolution. So we measure our fluxes both on hummock and hollow, and also we did another experiment where we take into consideration the difference between the total carbon emission, but also by removing the roots around the area. So that's why you can see here some of these plots where basically with the saw we cut roots up to 1 meter in order basically to collect CO2 that was mainly coming from the decomposition of peat, because carbon emissions are coming from the roots are not a net flux to the atmosphere. In the same way we breathe, and we exhale CO2, also plants do the same, right? They exhale, they can exhale, they exhale CO2 at night, right? But they, as you know, that CO2 is not a net flux to the atmosphere. So again, the importance of knowing modern versus old the carbon, the age of the carbon, because again, CO2 produced by the plants during the autotrophic process, as autotrophic respiration, is not a net flux to the atmosphere. What we are interested from peatlands is really to measure more what's coming from the decomposition, right, of the peat. So by removing as much as possible the roots, and so just be able to measure the decomposition of only peat, that allows us a much better refining, right, of the total carbon emissions. And then adding carbon 13, as I showed you in the previous slide, and carbon 14 really gives a very detailed nuance on the carbon dynamics from this area. So we had different plots. Of course, we had the intact forest, we have a drain acacia, and the rewetted acacia. So we wanted to show is really, how rewetting, how restoring acacia plantation, rewet them, how that is going to affect, carbon emissions. So we did this comparison in order really to understand the importance of rewetting. Of course, we had to compare it with our controls that were on one side, again, the intact forest, and the other ones, the totally drained acacia plantation. So we have these different sides. So if we start comparing here, again, undisturbed peat forest, you can see here drain acacia. Then you have also a mix of drain with shrub and the rewetted acacia. Kind of take-home messages is, of course, drained side had the highest total CO2, and the rewetted side had the lowest heterotrophic CO2. So that really show how rewetting is extremely important in decreasing the carbon emissions from this site. Here you can see difference in high end from hammock and hollows. Kind of this is the mean for the entire study sites for the four different sites. And as you can see, of course, the drain one is the one with the highest. In terms of methane, it's kind of the results, of course, are more complex, but still important. So, of course, methane emission is expected much higher, of course, in lowland areas, kind of more similar to kind of the natural forest. If you can see here, this is the control, right? And the rewetted here or the rewetted acacia area. Of course, you can see the rewetted acacia areas, the numbers are more similar to the forest. So this is actually what, we wanted with rewetting, increasing the water table and, kind of decreasing, of course, CO2 emission. But of course, as you decrease CO2 emission, of course, you're going to have more methane emission. But overall, if you look at the, of course, of both CO2 and methane together, of course, it's more important to have more methane and less CO2 than not the opposite, more CO2 and less methane. But while these results kind of perhaps not too surprising, you might say, well, we know more about this. I will experiment on, so these are the total, right? As I mentioned, looking at the total flux. But if we start looking and zooming in and looking at the experiment that we did on the microtopography and the trenching experiment by removing the roots, we can have a very interesting, more interesting, I would say, understanding of the carbon dynamics. And this is, I think, some of the key, I would say, the key difference compared to many other results, I think, that they just look at the total. So if we start looking at this kind of nuance on carbon dynamics, you see the importance of microtopography. So looking really is extremely important. One of the key results I would like to stress here is really the importance of when you do this type of measurement, looking at the spatial difference between hollow and hammock. We see that CO2 fluxes were about 30%, of course, lower in low hollows than in hammocks. So big variability, big difference. Within, we're talking about few meters. Within few meters, if you measure in one spot, you think you have a number and you think, oh, it's very high or very low. But actually, it's extremely important to look at both in order to not overestimate or to not underestimate, emission. Methane flux also were twice as high in this part, in the hollow part, here compared to the hammock. As you can imagine, the hollow part are closer to the water table and more wet compared to the hammock. If we look at then at the trenching experiment, that was be able to differentiate between total and heterotrophic, so autotrophic versus heterotrophic respiration. The heterotrophic respiration account for 40% of the total soil respiration. So that's different. If you think that if we measure, like imagine 100%, if you measure with automated chamber, normally we would assume that 100% is the total flux to the atmosphere. But of that 100%, what actually is really important is, again, what I mentioned is what coming from peat decomposition. And of that total is 40% only coming from peat decomposition, okay? When we look at the trenching effect on methane, we didn't find for methane statistically significant difference. We saw again kind of more like a, I would say, trend where we saw higher emission than in untrenched plot. But again, if you look at the numbers in terms of the standard deviation, 43 plus 115%, of course, it's extremely variable. That's why kind of it's hard to tell, because again, standard deviation is higher than the final number itself. But again, the implications of restoration for these results, especially if you look at the CO2, that when we do peatland restoration, we must consider really fine scale surface topography. This is extremely important. So we cannot think about an area as is all the same, because we would, the success of restoration, we might not have a successful restoration project in that area. Okay, so we need to look really at this microtopographic scale. Looking now again at the radiocarbon.
Sorry, Pak Max.
Yes.
5 minutes once, yeah.
5 minutes. Okay.
Yeah.
Okay.
Thank you.
If we look at the radiocarbon emission, as we saw for the aquatic component in the other side, we can see that, of course, in the drain plots, as you can see here, we have a much, of course, older carbon. Some of this is more than 500 years old. But the interesting thing is that once you rewet, this site, you can see that now the carbon kind of is changing. You have a mix a bit of some old carbons being released, but also you have modern carbon. So that means that rewetting really, by showing some of this younger carbon, it really proves that the processes, the ecosystem processes at the microbial level, there is a change in that. So we're going from microbes that had access only to deep soil carbon, now having access to, by rewetting the areas, having access to more modern carbon, liable carbon. So the microbes would always prefer to choose more liable carbon versus old carbon that is much more recalcitrant. So we show also that that when we drain acacia plantation, we really by removing this old carbon, we have carbon that will gonna be lost forever, because we know that it's taking thousands of years for new carbon to accumulate in peatland. Okay, so I move for the last 5 minutes of this presentation to another study. It was this experimental study that we call CHALPRE, where basically we control water table level by basically removing peat. That was the only way, of course, we could do it. We couldn't do the gradient that was done in April. So what we did instead, we removed peat in order, like terraces, in order to create this kind of terraces with different water table. And we measure, of course, carbon emissions and also vegetation. We were also interested to understand the vegetation that was growing back at different water table level. You can see here the different stages over the years, and also different experiment. I mean, I mentioned about the water table level, but also we did different experiment using meshes to simulate different type of shading. So what we saw, of course, is expected kind of the importance of water table in leading in kind of in controlling, CO2 emission. But this is the first study ever on tropical peatland done with the automatic chamber. So we had 24/7 automatic chamber measuring this for 2 years. And so this will be the first data set on tropical peatlands for such a huge amount, long-term data. Again, kind of proving many of the things that we always thought from other studies, from manual studies. We have really detailed study on this, proving this. And the same for methane. While of course for CO2 it's extremely linear, the correlation is very nice. For methane is a bit much more complicated, so the patterns are a bit less consistent. The last slide I would like to show you is come from the vegetation experiment where Al Hoyer is involved, of course, as the main PI for this part. But the very interesting, I would like to show you because the findings are extremely interesting. We saw that the best growth condition was the water table between 0.2 and 0.4 below the surface. And this is very interesting because normally we always, think about rewetting right away is the best thing to do in order when we want to restore an area. But in terms of what's happening for the seedlings, actually, if you rewet right away, we saw where we see the highest mortality. So clearly, the plants need some the water table to be a bit lower in order to survive. So this is one of the kind of key funding. Also, the importance of shading. We saw the partial shading benefit many species. So the interesting part that was actually some of the acacia trees, despite being, of course, not the original peat swamp, endemic species, but they actually did help in creating shade for other species to come in. So despite again acacia not being endemic from peat swamp forest, they really help with their shading to create microclimates for the seedlings to grow. So again, this is kind of extremely important results. I mean, of course, it's just one slide. The paper is in preparation by Maya Lampela. Hopefully, will be submitted maybe in the next few months. But I wanted to show you, even if it's not kind of detail, kind of results again for time. But I think it's extremely important to consider that for the plants, it's important to start a bit kind of with the lower water table, and then slowly, once you have different species that can, once the seedlings kind of gets bigger and bigger, and so then can sustain higher water table. So the water table should be increased only at the later stage, because really we need first the seedlings to survive, and then also take into consideration the shading is extremely important. These are the kind of some of the first data really showing this. So this kind of course has implication in terms of course, restoration project. Again, key conclusions. You can see here some of the things that I mentioned before, starting from the first paper from Sigit on nature communication, the importance of conserving impact peat swamp forest, the importance to prioritize rewetting over a passive restoration. Also trying to integrate, radiocarbon and stable isotope to improve our understanding of carbon sources, to kind of really help a better national reporting. Include microtopography in restoration planning. This one again one of the key results. And these are all the policy relevance of some of these findings that hopefully you will find useful. Supporting for NDC, enables result-based payment, underpin nature-based solution, guides restoration planning, and improve MRV system. Again, there is much more. I hope that already show you so many kind of results. I hope you are not overwhelmed. But again, if you have any questions, I mean, of course, we have now a session for curiosity you might have. But of course, before ending, I would like to thank, of course, my postdocs that now they grew up, and so they have their own position. Pierre, data that I showed, and now is at TU, Sigit, now at James Cook University, and of course, the other PIs. Sanjay and Prof. David Taylor, and of course IP Bay University, Temasek Foundation, and April and IPMP. And I think with this I will end here. Okay, thanks for your time.
Okay. Yeah, thank you very much, Pak Max. Yeah, for the incredible and remarkable presentation. We have so many a lot of information and also insight presentation and information, new knowledge as well regarding carbon dating, using carbon dating for measuring the emission, and also not only the soil, but also the biota, the microbes as well, who are responsible increasing the gas methane and carbon dioxide. So, well, now is the time for the discussion. I'll give the audience the opportunity to ask question. I think the first question will be given to a participant who raised their hands. Anyone who has a question and would like to have a direct conversation with PAMEX?
I mean, I see a first question from
Chat room?
Yeah.
Yeah. In chat room, yeah. Okay.
So, to what extent does the current scientific understanding of greenhouse gas dynamics in rewetted tropical peatlands adequately inform restoration policy given the trade-off between? I mean, that's a very kind of good, of course, good question. At the moment, of course, we treat these areas as if there was all the same. So if you think about the knowledge of our emission factors by land cover type, sometimes we use one number for an area that is like millions of hectares, right? And we use that one number. Of course, I would say that some of those numbers, some are better than others. I mean, if we look at some of the numbers we have from oil palm plantation, there are lots of data out there, especially for plantation where the microtopography is not that clear, because of course, in order to set up your plantation, right, you have to go with the tractor and you remove a lot of the micro topography, right? So of course, in areas that are kind of more flat, kind of homogeneous, some of those numbers I think are kind of much better. But when you start having different micro topographies, as our data kind of showing in some of our land cover types, I mean, some of those numbers are quite, I would say, are quite off. So I think there are new kind of recent studies, and some of these studies probably, hopefully, will also go in some of this report. We are kind of updating some of these numbers. So there is one project now that also some my Indonesian colleagues are involved. That is with the FAO. It's called Peatlands. And basically, this report has just been written where we are kind of updating emission factors. And of course, we have new numbers that are much more detailed compared to, because we have data for the last 10 years that we did not have before. Okay. So this report will be released probably in the next 6 months. Was involved in this project and involved people from Southeast Asia, Central Africa, and South America to kind of update these numbers. Because once you have these emission factors for these different land coverage types, of course, then policymakers, right, and people doing reporting will use those numbers and will be much more accurate. So I would say the current knowledge, the improvement we did over the last 10 years is really a lot. We did a lot in terms of improvement. There's, great science coming from Indonesian scientists, Malaysian scientists. I think actually we have more lack actually of understanding from underrepresented areas in Cambodia, Philippines, because imagine that they're using numbers coming from Indonesia, but they don't even have peatland forest in Cambodia. They don't have trees. It's more peatlands from graminoids or like it's very different. So in that case, you can imagine the number they use are really off, even worse. So the better number we have are of course coming from Indonesia and Malaysia for data from the last 10 years. So I think with some of this new report that will be released soon from FAO, we'll be able to inform policymakers even more. But at the moment, some of those numbers are a bit off. Okay, next question. How to restore? I'm reading from the chat. How to restore the gray peatlands with peat surface subsidence and peatland with already reversible drying. I mean, I think that's a very valid question. I mean, based on our data, at least, I mean, of course, one thing to keep in mind, and that is what I've learned by working on different sites, is that sometimes we tend to we see something on a paper, so this is very good data, and then we try to use that those results in a different site, right? So I think what is extremely important is knowing the local conditions. So this is, I think, one of the key things I think I learned by looking how different each site is, right? So it's extremely to understand the local conditions. Said that, based on the data from, let's say, our APP site, from the subsidence data, we have 6 years of data from from all. Of course, rewetting is a key, right, to stop the subsidence, right? The main issue is that, as you mentioned here, you talk about irreversible. But I would say more than reversible drying. Sometimes I will talk about when I read the word irreversible, I think more about the irreversible carbon as well. The main issue is then if you just re-wet, right? Of course, you lost, of course, that carbon, and that's why the drying maybe you want to connect it with the reversible lost carbon. But the issue now that we have is trying to recreate a system where new carbon is created, and that means where you are able to recreate new peat, right? I think that's one of the key thing, because once, okay, you can stop or you can slow down, let's say, the substance by rewetting, but the issue is now, are we able with the restoration now to recreate a functional peatland forest where you have new input, new carbon input into the system? So only at that point, probably, I think we can say that we actually restore completely, the system where you have, I mean, I'm talking now just about carbon dynamics. Of course, we have to talk about biodiversity. It's a big picture, but normally if you have a system where you have an increase in biodiversity, you also have a system where with a functioning forest, of course, you're gonna have also a system where you have new carbon being inserted, in the system to create new peat. So, of course, this is part of all a big picture. I mean, I'm focusing as an expert, of course, in carbon dynamics, but I cannot. I need to think about the bigger picture and how everything is connected. So, if you have you have a functional forest, to me means that you have a good biodiversity, almost close to the original. So both in terms of flora and fauna, and then once you have a functional ecosystem, I would imagine you have also new carbon, right, that will get back into the system. So of course, by just rewetting, you're just gonna slow down things. Yes, but it's not. You cannot say, oh yeah, the system is restored. To me, we have to be a bit kind of cautious when we use the term. It probably is less degraded, right? Definitely. Kind of we're trying to restore, but the road to restoration, the full restoration, it's a lot. It's not just only by rewetting. It's really by recreating a functional ecosystem. I think that's where to me, you can say we can achieve restoration. It's kind of really creating a functional ecosystem. In this case, a functional peat swamp forest.
Thank you, Pak Max. A very important message.
Yeah, because I mean, if you think about even what I show in these results, is really to take into consideration uh, the micro scale. This is kind of one of the key, I would say, key message in terms of restoration. The microtopography, I showed you the importance for the carbon emission, but the microtopography is also important for plant development. Because you have some, of course, you're gonna have some seedlings that will be able to grow in more wet or drier condition, right? So it's all linked. So it's all linked for different reasons. Of course, here I'm trying to answer some of these questions, even if I'm not an expert, of course, in biodiversity, but I think I'm trying to go, in my opinion, with an open mind and kind of at least knowing the bigger picture, even if you're not an expert in that, but maybe then asking to the expert in the respective field is extremely, I think it's extremely important. Okay, there is.
Yeah, there is one audience raise hand, Ibu Siti Sundari. Yes, please, Ibu.
Oh
Please
yeah,
unmute.
okay, thank you, Bu Esti. Oh, thank you very much, Pak Max. I am Siti Sundari from Research Center for Ecology and Ethnobiology, the same research group with Bu Hesti. I have a question about carbon aquatic pathways in your presentation. I really interested about DOC, DOC export, especially in the groundwater. How about your methodology? This is only for acacia plantation. How about if we want to apply it to for a natural pit swamp forest or undisturbed, and also for disturbed pit swamp forest?
Yeah, the
Can you explain
methodology.
to me?
So the methodology is exactly the same. I mean, for this site, we focus only on the plantation. But on this site, also on this side, we focus on the plantation. But you can use the same methodology in also on intact forest. So the idea, of course, in the intact forest, I mean, perhaps you would not. The only thing you might not use as much, you can see here Jared measuring diffusion carbon fluxes from kind of the canals. Of course, you don't have canals in the forest, but in terms of the methodology, what we did, I mean, let me show, maybe it's clear from this photo. Basically, what you would do, you would set up wells, as you can see here in the plantation. On again, you would place it perhaps take into consideration also microtopography, hammock hollows in your area of interest, let's say in the forest, and you would measure, of course, water table level and collect. With the way you do it, basically you have a tube. You put the tube in the water, and then with the syringe, you collect your water sample, and then you put in from your syringe. You have a filter, and you filter that water into a simple vial, and then you will measure from there. You can measure, you'll measure DOC. That's one thing. Then whatever is left on the filter, that would be your POC, that is the particulate organic carbon. So DOC, of course, is the one that passed through the filter, that is 0.4 micrometers. Whatever you have on the stuck on the filter will be your particulate, but based on our data, we didn't measure POC. DOC was the biggest component. So let's say if you don't have too much money to do both measurement, DOC probably would be more important than POC. Then, of course, if you can measure both, that would be ideal. Then the tricky part, and this is quite cheap, I would say, analysis for DOC. The most expensive part is measuring the CO2 and methane in solution. So we had one device that we place it in the canal that could measure the real time, but you can also measure it manually. But you will need a GC for that. So in this case, as I mentioned, we were interested to do long-term monitoring, so we have it inside the canal. But you can still collect your water sample, put it again in a vial, some specific chemicals. But then you will sample from the flask the top layer with the syringe, and then you will need a GC. It's just much more tedious because, of course, you need to get lots of vials because you want to measure it over a specific period of time. So there are I mean, depending again on the budget available, I would say the kind of more basic is at least measuring DOC, POC, then having access to a GC, then you can get take manual samples, but then you need a lot of vials. Then if you have more money, then of course having the device that measure it all the time. So there are different, again, depending on the budget, different way of doing that. But at least I would say the DOC, that's kind of the bare minimum. Of course, we measure DOC and dissolved CO2 methane, and of course, it gives you all these deeper nuances that I showed you, right, in this slide. But otherwise, again, it depends on how big is your budget, but you can still collect the samples manually if you don't have access to long-term monitoring device. But again, for carbon-13, you still need to measure manually anyway. So one thing is measuring concentration. That is, of course, is a bit cheaper. But then carbon-13, that's much more expensive. I mean, we just recently got 2 years ago, a stable isotope analyzer, IRMS, in geography. So now I'm very happy, of course, because I can measure as much as one. But there are now, of course, there are many of those IRMS. So I think there are a couple of, I think I know in Indonesia there are a few, but of course, it's, of course, you have to send the samples and so on. So having carbon-13 also will give you all this extra information that I think it's valuable, but it's a matter of like everything for researcher on the budget. But I would say the bare minimum is the DOC and POC. That's the cheapest. Then carbon-13 and dissolved CO2 methane. That's the more expensive because you need access to GC and IRMS. The good thing is that, of course, through project and collaboration, of course, I measure lots of Indonesian samples with my collaborators in Indonesia. So, if when you work together with other university, then it's easier to exchange, to send samples, right? Because of course the cost is covered with the grant. But I mean, you know these things, right? So it's a matter of having the right team with each team having the right device that you need to answer your research question. Otherwise, there are potentially, of course, there is a budget. There is potential also to send the samples just for analysis, like if you to pay, So there is also the option.
Yeah, thank you very much, Pak Max. Makasih, Westi.
Yeah, okay.
Sama.
And one question in the chat room is from Resti Ora. She asks about what are the technical challenges in peat restoration, particularly in maintaining a high water table, and how important is the integration of isotope and radiocarbon based on a base MRV system in national and global climate reporting.
Okay, so I can answer a bit the first question, and then I will focus on the second. The first, of course, I mean, I know what I know is based on what people doing that told me, right? And they told me that it's extremely people working, in plantation. They told me that it's so difficult to maintain a high water table because the issue is that everything is connected, right? If you look at a pit, we divide peatlands in a peatland hydrological unit, right? So, and because everything is connected, it's extremely difficult to maintain the high water table. So I'm not sure I can answer that properly in terms of from a management point of view, where to put the dams and things, but it's clearly an issue of where you place those dams. But again, I don't know why it's so difficult. We would imagine, you just block it and then the water table magically, will go up. But apparently, based on people doing this job, is extremely complicated. Again, because we're talking about almost like a living ecosystem where and water is connected everywhere within the pit dome. So you need to do basically your hydrological homework very well to have a successful area where you raise the water. But for as concern your second question, how important? I mean, based on what we have seen, I think it is important to understand that one of the main problems becomes the cost, as I just mentioned with my previous question. I mean, this is important because it really gives you also, I gave you a general idea with some of my results. It gives you a nuance, really like a more detailed understanding of what's happening. So the more you know of what's happening, the more you are able to address the issue. What we've seen based on data let's say on radiocarbon, right? For example, we can see that as the area gets more and more degraded, that means that the water table is lower and lower, right? Because more of this old carbon is released, right, in solution, right, in the aquatic component, and so that'll give you a level of understanding on how degraded is the area. So there was also we had a talk with some colleagues a few years ago on a project that unfortunately we didn't get funding, but the idea was basically really to create an index on using isotopes on the level of degradation of an area. So basically, by knowing a specific number, let's say you can tell you, oh, it's moderate, heavily degraded, right? But of course, you need access to multiple sites, of course, with different level of degradation, and try to create this index based on atoms. This was something that kind of we had a discussion with also with colleagues, but unfortunately never got funded. But perhaps maybe it would be a good time to kind of rewrite the project. But that could be quite interesting if is possible. I don't know if it's possible. That was, of course, just an idea based on the publication of what we've seen from, of course, the different sites and how much by knowing basically these numbers, how it can tell us about the level of degradation. But of course, you want to have a number that is indicative of that area. So you can imagine it would be so nice. You get a sample, you measure radiocarbon from DOC, you apply this potential index and say, oh, this is this level of degradation of that would be quite amazing. But it's still, even if we don't have that magic index that I would like to create, it still give you an idea of, okay, there is degradation going on this side, because in a site that are not degraded, you will not see old carbon being released. You will just see modern carbon, because the microbes would just eat what's released, was the fresh carbon that is released, let's say, from plant decomposition or so on, rather than using this old carbon. Because this old carbon, we have to remember, is a very recalcitrant. So microbes would not choose to eat that. If you think about, just to give you an idea, this idea I give to my student, if you have a toast, and you burn a toast, and you wouldn't eat the black stuff that is on your toast, right? And for the microbes, it's the same. The microbes would prefer to eat the fresh part of the toast and not the burnt carbon that represent the old carbon, right? So that would be the last resource. They always prefer, because it's from a it takes much more energy, to decompose the old carbon, because of the recalcitrant, based on the chemistry of the carbon compared to the label carbon. So it's really this pure physics. So having access to this in reporting would be useful. At the moment, again, it's a bit patchy. It's like we have information, but we don't have a way that is really organized and with indexes, where we don't have that yet, but we are showing with some of these first results that is important. I hope that answered your question.
Yeah, this from Bagus Tony, and he asks, the Indonesian government has designated 30% of peatland within a peat hydrological unit for protected function. Is this sufficient to minimize peatland carbon emission?
I mean, this is a difficult question to be honest. I'm not able, I don't think I can answer. But again, the issue to answer this question, I will go back to what I mentioned before about, how peatland, how is everything is connected, right? And also our data show that basically we have an area, right? What is our site? You can see my slide, right? So by looking at this data, right, from our data, so technically, right, we have here the degraded area, and then the rewetted area, and here you have the forest, right? So you mentioned about this 30%, but you can see that even within a kilometer here, so this is about, I think, a kilometer of intact forest, right? It's still affected by, the degradation that is happening here. So, I mean, let's say it helps. Yes, of course it helps. But then saying that, I mean, I would call this is still a degraded area, right? Despite, if you look just at the distance. So things 30%, 40%, I mean, I think these numbers are kind of very specific. So I'm not able to say, oh, it should be 40% but I think the data definitely shows that even if you have a drain area and then all the rest around is rewetted, the rewetted area around will still be affected. So then, of course, how much you have to go inland to say, let's say you have a buffer zone, let's say, I think probably would be better to have a buffer zone in between the rewetted area. I mean, this is a really difficult question. I don't think, I mean, I don't know what that 30% was based on, how they calculated it. So I'm not sure, but I think even our data shows that even if you're a wetted area, you have a degraded area and a wetted area, still for kilometers, the forest will still be affected by the change in hydrology. So I guess that what we have and is better than nothing, probably. But I'm not sure if that 30% is enough. Probably should be more, but I cannot give cannot give a number, unfortunately.
Okay, yes, thank you, Max. Yeah, because if we have evidence from the research, then we can also give a better recommendation for the government to improve the peatland management in Indonesia.
Yeah. So,
And
for sure that this data, once they're up, we already have a few paper published, but there's this other data that we are kind of preparing, for publication. I think those will be quite also useful for the government, I think. So hopefully soon, hopefully we'll publish.
Okay, yes, great, thank you. And I think it is almost to the end of the expert talk. Yeah. And all right, what we can conclude from today's discussion, emission are not only from the deforestation and fire, but also from long-term decomposition of soil carbon pools. Conserving intact peats from forest can prevent about 86% of the carbon emission of the region, and restoration, both rewetting and revegetation, can also mitigate numbers of emission. So therefore, protection intact peats from forest is crucial as the peatland restoration and climate change mitigation action. And finally, my deepest appreciation to our resource person, Dr. Max, who have shared his knowledge, insightful ideas, and policy recommendation. And I would like to invite to Dr. Max to give a closing statement. Thank you.
Okay, thank you. Well, thanks for having me. It was a kind of real pleasure to share, my latest results from our in-prep group to you guys, and I hope really that once published, this data will be useful of course, for the Indonesian government. That's kind of why we're working so hard, hopefully to improve peatland management and livelihood. Thank you.
Yeah. Yeah, I hope we can meet in the Asia Flux on October. Yeah, hopefully.
See you there, hopefully, many of you.
Yeah. I also appreciate all the participants who have attended and listened enthusiastically. And once again, I thank to the speaker and audiences, and I will hand over to the session to the MC, Pak Buki. Thank you.
Terima
Thank
kasih.
you very much, Bu Hesti. On behalf of the organizing committee, we would like to express our sincere appreciation to our moderator, Hesti, for skillfully guiding today's first expert talk. Thank you for your excellent moderation, for keeping the discussion focused on engaging, and for ensuring the session ran smoothly from beginning to end. Ladies and gentlemen, as we come to the end of today's event, we would like to take this opportunity to express our sincere gratitude to our distinguished speaker, Mr. Massimo Lupascu, PhD, for the inspiring and insightful presentation. To show our appreciation, we would like to present a token of appreciation in the form of a certificate and a plaque symbolic to him. May we kindly invite again Bu Hesti to present the token of appreciation. Time is yours.
Thank you. Pak Max, as of appreciation from us to you as a research person for the expert talk of the Research Center for Ecology and Biology, we have a certificate here and we'll hand over to you.
And yeah, and yes, please. And this is a e-certificate, and another one is a token appreciation, and we will send to your address because it is what is called the token appreciation and plakat in bahasa Indonesia. And for the closing remarks, representative of the head, the chairman of the Research Center for Ecology and Ethnobiology. So I would like to thank the speaker, Max, distinguished and honored guests. And as we conclude the seminar on Draining the Past, Rewetting the Future, Dynamic Greenhouse Gas Emission, I would like to express our deepest gratitude to our esteemed speakers for sharing their valuable insight and expertise. Today, we have explored the critical role of peatland management in mitigating climate change and the importance of rewetting and restoring degraded peatlands. As we look to the future, it is clear that our collective efforts are crucial in reducing greenhouse gas emission and promoting sustainable land use practices. Let's continue to work together to protect our environment and ensure a more sustainable future for generation to come. And hopefully, we from Research Center for Ecology and Ethnobiology and NUS will have research collaboration in the future, hopefully. Thank you once again to our speaker, organizer, and participant for making this webinar a success. Let's stay connected and continue the conversation on how we can work together and to address the pressing issues of climate change. Thank you.
Terima kasih banyak. Thank you, everyone.
Yeah.
Bye.
Thank you very much.
Yeah.
Thank you very much.
Thank you.
The next expert talk. Stay safe, stay healthy, and keep making a difference. Thank you and goodbye. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Santi, Santi Om, Namo Buddhaya, Salam Kebajikan. Thank you very much all.
Thank you very much.
Thank you, Om Bugi.
Bugi.
Thank you very much.
Terima kasih, terima kasih. Alhamdulillah, trust semua.
Bugi look so
Ke
handsome.
Mbak JG, mangga. Zoom.
Terima kasih.
Terima kasih semua.
Terima kasih semua ya. Sukses selalu.
Halo Pak Bugi.
Minum nggak minum nih?
Iya, sudah bisa minum malu ada video.
Mana Pak Bugi tadi? Astagfirullah.